Now in A, we want to show that the total claim size is a compound Poisson process. So what we want to do is we want to show that the total claim size has, well, I think it's best to write it this way, has the same distribution as a process of IID claim sizes y tilde I summed up until the n tilde's claim size, where n tilde is a Poisson process with arrival rate 1/2. So that's actually given as the sum of arrival rates for the two lines of business. And where we also want to show that the claim size in this new in this compound process, it has tail distribution given by the mixture of the two tails in each of the lines of business. So the way we're going to go about this, well, there are many ways of going about this, but I think one of the easiest ways is to work with the moment generating function, because we have actually done an exercise, I think in the first exercise set. So recall that. So we did an exercise in the first exercise set where we actually calculated the moment generating function for a compound Poisson process. So recall that for a compound Poisson process, let's just say it's the sum of what should we use? There are so many letters that we're already using, so let's just say compound Poisson process, sum of wi from 1 up until nt. We have that the moment generating function is given by kappa of alpha equal to e to the lambda, where lambda is the arrival rate of the Poisson process nt. So e to the lambda multiplied by the moment generating function of the claim size evaluated in alpha minus 1, and then you multiply the entire thing in the exponent by alpha. So we have this result, and therefore, since we know that this is compound Poisson and this is compound Poisson, then we can find the moment generating function of each of these using this formula. So let's just write up. So let's start by calculating the moment generating function of the left-hand side. So note that the mean value of e to the alpha multiplied by this entire thing here. So you have n1t yi plus n2t zi. Well, first of all, since the lines of business are independent, we can split this expectation into two products. So you have e to the alpha and then the total claim size on the first line of business multiplied by the moment generating function of the total claim size on the second line of business. Okay, so that's nice. And then what you have here is just one moment generating function of a compound Poisson process, and in the second one here you have the other moment generating function on the second line of business. So we use our formula for the moment generating function of a compound Poisson process, and what you get is e to the alpha multiplied by lambda, and in our case the claim arrival rate is given by one quarter from the exercise notes, 1/4, and then you multiply this by the moment generating function of y1 of alpha minus 1, and then we multiply that by this moment generating function here, which is e to the alpha divided by 4 as well, and multiplied by the moment generating function of the heavy-tailed claim evaluated in alpha minus 1. So what we want to do is we want to manipulate this expression in such a way that we end up with a new expression that reminds of a moment generating function for another compound process. So if we want that, then we want to end up with an expression where you have e to the alpha and then multiplied by something multiplied by some other thing minus 1, where this something will then be the claim arrival rate in our new compound Poisson process, and this something should then be the moment generating function of the claim sizes in our compound Poisson process. So let's just see what we have up here. Up here you have alpha divided by 4 multiplied by this minus 1, alpha divided by 4 multiplied by this minus 1. So you still have the alpha divided by 4, and then you can just gather everything inside, where you have kappa y1 of alpha plus kappa z1 of alpha. So you have two moment generating functions, and then you have minus 1 minus 1. And what you get in here is you actually get a minus 2, right? So we can see that this is equal to e to the alpha multiplied by 1/4 multiplied by kappa, so the moment generating function of y1 alpha plus the moment generating function of z1 alpha minus 2. However, what I really want in here is something minus 1. I want some kind of moment generating function minus 1. And what we see here is this is not a moment generating function, because this is a moment generating function and this is a moment generating function. And if you just add two moment generating functions together, that doesn't work out here. And also this is not minus 1 as we want. But the way you can get this to become minus 1 is by dividing this entire thing by 2 and then multiplying with a 2 outside. So you have e to the alpha multiplied by 2 divided by 4, and since you multiply by 2 on the outside, you divide by 2 on the inside, and then you get 1/2 multiplied by the moment generating function of y1 plus 1/2 multiplied by the moment generating function of z1 minus 1. And what we can now notice is that this is the moment generating function of a compound Poisson process. I'll just write CPP. That stands for a compound Poisson process, where the arrival rate, with arrival rate given by this thing here, with arrival rate 1/2, and where the claim sizes have the moment generating function 1/2 multiplied by the moment generating function of y1 plus 1/2 multiplied by the moment generating function of z1. So the last step that we need to finish up here is just to figure out what is the distribution of the claim size in this compound Poisson process when we know the moment generating function looks like this. Now, since this is the weighted sum of two moment generating functions where the weights sum to 1, then this is actually the moment generating function of a mixture distribution. With tail distribution given by 1/2 multiplied by the tail distribution function for y1, and since y1 was exponentially distributed, this is e to the minus x, and what you have here is 1/2 multiplied by the tail distribution in by the tail distribution for z1, which was given as 3 divided by 3 plus x to the 4th, I think, because in the line of business that was heavy tail, yeah, we had that the claims are Pareto distributed with parameters 4 and 3. So by using the moment generating functions, we have now concluded that our total claim size, let's just write that up. So we have concluded that the total claim size expressed as such and some other compound Poisson process expressed as such. So we have concluded that these two things have the same moment generating function, and therefore our total claim size is compound Poisson process with arrival rate 1/2 and claim size distribution given by this thing here. So we'll just say given by star.